This video is one of two educational videos about defects in silicon solar cells. It's split up into two parts. For those interested in a brief overview of defects, check out this movie, Part 1. For those interested in a more advanced way to explore defects, check out Part 2. In Part 2, we will explore the impact of defect parameter inputs in a solar cell modeling software called AMPS. AMPS stands for Analysis of Microelectronic and Photonic Structures. The free version that I will be using can be found at this website shown here. Welcome to Part 1, a brief introduction to defects, intentional and non-intentional. In 1 cubic centimeter of intrinsic silicon at 300 degrees Kelvin, there are about 5 times 10 to the 22nd atoms. For solar cells, silicon needs to be about 99.9999% pure. Defects and other impurities need to be on the order of parts per billion total. So let's start from the basics. What types of defects are present in solar-grade silicon today? Usually we think of defects as unintentional. These can be impurities or also crystallographic defects. Impurities are atoms other than silicon present in the lattice. There are also crystallographic defects. These are disruptions in the perfect silicon lattice. Silicon has 4 valence electrons, thus, in crystal form, covalently bonds to 4 other neighboring silicon atoms. A perfect silicon crystal has a diamond-like structure, which is 2 interpenetrating face-center cubic lattices. Let's take a closer look at crystal defects. These can be 0, 1, 2, and 3-dimensional. I'll focus more on 0 and 1-dimensional defects. 0-dimensional are also called point defects, and 1D are line defects. Picture the silicon crystal lattice in 2 dimensions, so we can easily visualize these defects. At any lattice point, if an atom is missing from where one should be, we have a vacancy. Vacancies are formed when atoms are removed from their position in the lattice due to thermal fluctuations. These are also known as Schottky defects. When there is a vacancy in the lattice, we end up with dangling bonds because of the 4 neighboring silicon atoms. An interstitial defect is present if there is an atom found in part of the lattice that should be void. See the extra atom squished into the lattice? We can also have a combination of a vacancy and an interstitial, which is known as a Frankel defect. So here, there's a missing silicon atom, but it ended up somewhere else in the lattice that it shouldn't be. Sometimes we have a non-silicon atom, or an impurity, that creates the defect. For example, substitutional impurity is an atom that replaces the silicon atom in the lattice. There's also interstitial impurities, in which an impurity atom is squished into the lattice where there shouldn't be any atoms, like the interstitial sites. These small defects can cause 1-dimensional defects or dislocations. A dislocation is a lattice distortion along a line because the boundaries of 2 regions of the crystal are perfectly crystalline themselves but are misaligned with each other. These could result in an edge or screw dislocation, like these. 2-dimensional defects can propagate in the form of grain boundaries. These are present at the interface between 2 crystals with different orientations. This causes a disruption in the periodicity of the lattice structure. Monocrystalline or single crystal silicon means we have no grain boundaries. So how can we control these defects? How can we produce such pure silicon? How can we make single crystal silicon? Well, more often than not, impurities are created during processing. The most common method for producing silicon ingots is Czochralski growth, also referred to as CZ growth. CZ growth in principle is very simple and can be used to produce large volumes of monocrystalline silicon. However, it requires very high temperatures, so it is rather energy-intensive procedure and can be relatively slow. The process works by starting with a single seed crystal of silicon in a molten silicon bath. The seed is slowly drawn from the bath. The temperature outside of the bath is just low enough that the molten silicon surrounding the seed crystallizes while it is coming out of the bath. Since the drawing rate is slow, the molten silicon crystallizes in the same direction or orientation as the seed crystal. This helps produce a single crystal without grain boundaries. During CZ growth, if the seed crystal is drawn too fast, or that outside temperature is too low, crystallographic defects will form. However, impurities from CZ growth are mostly caused by the silica crucible. CZ growth introduces a lot of oxygen impurities, on the order of 10 to the 18 oxygen atoms per cubic centimeter. During crystal growth, unintentional impurities can form. This is also when intentional impurities are introduced. Intentionally adding impurities is called doping. Dopants are technically defects because they are non-silicon atoms in a silicon crystal. However, we need to dope silicon to create that p-n junction. Without controlled doping, free carriers can be generated in intrinsic silicon, but there's no potential gradient to provide a driving force for electrons to go in one direction and holes to go in the opposite direction. Silicon is typically doped with group 3 and group 5 elements. Group 3 elements are electron acceptors, while group 5 elements are electron donors. Introducing these electron acceptors creates p-type silicon, and adding electron donors creates n-type silicon. Silicon atoms in the lattice are replaced by these dopant atoms. The most common dopants for silicon are boron and phosphorus. The key is to use atoms with valence states just above or below that of silicon so that we can create electron excess or electron deficiencies. Doping densities typically range from 10 to the 13th to 10 to the 20th atoms per cubic centimeter. For n-type doping, we use elements with 5 valence electrons, like phosphorus. When phosphorus replaces silicon in the lattice, the neighboring silicon atoms will only provide 4 valence electrons for covalent bonding. The extra 5th electron on phosphorus is now free, and it adds to the majority carrier concentration. And it also leaves behind a fixed positive charge in the lattice. Likewise, for p-type doping, we use an element with 3 valence electrons, like boron. When boron replaces a silicon atom in the lattice, it can only provide 3 valence electrons for covalent bonding. This leaves one of the silicon neighboring atoms with a dangling bond, or a hole. This hole can move from atom to atom as electrons come in to fill it. Mobile holes add to the majority carrier concentrations and leave behind a fixed negative charge on the boron. Dopants are introduced either in the melt silicon, like in CZ growth, or it can be introduced after crystal growth with vapor methods that allow dopants to diffuse into the crystal. From this video, we've learned that defects and impurities are created during processing. Whether they are desired dopants or accidental impurities, they occur during some step in fabrication. And there are so many steps involved with building a silicon solar cell, and a lot more processing involved that was discussed in this video. If you are interested in modeling defects and understanding how they can impact silicon solar cell performance, check out part 2 of this video where we will explore these defects in AMPS modeling software.